In a sequence, when we talk about n, what we mean is the position of each term in the sequence, each number in the sequence. So in the sequence above, which is 5, 6, 7, and 8, 1 means that 5 is in the first position, and 2 means that 6 is in the second position, and so on. When we say we want to find the nth term of a sequence, what we mean is this. We want to find a formula so that if I told you what the position of a number is, you could tell me using that position what the actual number is itself. So usually the way to do this is to look at the numbers, so 5, 6, 7, and 8, and their connection with their positions. Now in this case, there is a connection. And if we wrote the connection down in words, it would look like this. Number equals position plus 4. Because we can see, for example, that 5 is 4 more than 1, and 6 is 4 more than 2, and so on. So each number is its position, but with 4 added. But we don't want to write this formula using words. What we want to do is we want to write it using algebra. And so that's the translation we have to make. So for example, the number, the bit, I'm going to write as the nth term. So that just means the number we're interested in. The position of the number is n. N stands for the position of the number. And then we just add 4. And that's the answer. The formula for each term in the sequence is its position, which is n, added to 4. So for example, if somebody said, well, I really want to know what the 72nd term is, 72 is the n in this example. So the 72nd term would be 72 add 4, and that will give you 76 as your final answer. If we look at the numbers 8, 10, 12, and 14, if we want to find a formula for the nth term of the sequence, it's going to be more complicated. It's more difficult to make a connection between 1, 2, 3, and 4 and the numbers above. Now, if you spend some time thinking about it, you'd almost certainly be able to guess the answer or work out the answer, but there is a shortcut way we can take for questions like this. So if we look at the numbers above, we can see that when you go from the 8 to the 10, you add a 2. 10 to the 12, you add a 2. 12 to the 14, you add a 2, and so on. Now that difference, that plus 2, tells me that in the formula for the nth term, there must be a 2. The 2 comes from the difference above, and also that 2, it's going to be multiplied by an n. And that's going to be part of the formula for the nth term. The only problem is that's not all of the formula. Because if we try this formula, so say for example, we thought about what happens when n equals 1, then we would get that the first term would be 2 multiplied by 1, which is equal to 2. And the first term is 8, so that's clearly completely wrong. So what we need to do is we need to adjust the 2n formula to make it work. Now, the adjustment is just an adding or subtraction of a number. So the first term, if we use 2n is 2, we want to make it into 8. So what we do is we just add a 6, like that. So the nth term formula actually is 2n plus 6. Again, it's important to realize that if you look at each part of this formula, it comes from somewhere. So the n's going to be in the formula somewhere, obviously, but the number multiplying the n, the 2, comes from the fact you've got this constant difference at the top of 2. And if the constant difference was 3, it would be 3n. If the constant difference was 5, there would be a 5n in the formula. The adjustment bit, the bit at the end, we got by just thinking about the first term. And we could see that the first term was equal to 8, not equal to 2, which is what you would get if you just used the 2n. So we added the 6 just to make the formula complete, to make it work for the first term. Although we can see this formula works for the first term, it'll actually work for any term in the sequence now. So for example, say you had n equals 3. Well, for n equals 3, we would get a third term equal to 2 multiplied by 3 added to 6, and that equals 12, and that's what we want.